In this video, we're going to learn how to draw Lewis dot structures for ionic compounds. So one key thing to remember about ionic compounds is that they form by electron transfer. Electron transfer. And so what we usually see is that the metal is going to give electrons to the non-metal because the metal is less electronegative than the non-metal is, meaning that the metal doesn't attract electrons as much as the non-metal does. So if we take a look at the quick formation over here of sodium chloride, we have a sodium metal atom and the chlorine non-metal atom. Sodium, being less electronegative, will lose its electron to the chlorine. And so what happens is that the sodium now has a positive charge, +1, because it lost one electron, and the chlorine has a negative charge, -1, because it gained an electron. And now that they have opposite charges, they attract each other, and as a result, are bonded to each other chemically. And so that there is the ionic bond. It's the attraction between the oppositely charged ions. So after the transfer happens, our ionic bond can actually happen because the positive and negative ions are held together by their electrostatic attraction or force. So usually an ionic bond is going to form between a metal and a non-metal. So if you see a metal and a non-metal, usually you're going to have an ionic bond there. How do we know for sure if we have an ionic bond? Well, we need to use what's called the electronegativity difference. So this here means delta. Delta means change in electronegativity. And so if the electronegativity is greater than or equal to 1.7, then you know that your bond is ionic. Essentially, electronegativity means the ability to attract electrons. So the higher the difference in electronegativity means that one of them is so electronegative that it's just going to rip the electron away from the other one. So it needs to be high enough for that complete transfer to occur. So let's just do an example. Let's make sure that NaCl actually is ionic. So what we do is we go find the electronegativity values in the periodic table for sodium and chlorine. So here's our periodic table. Sodium's value is 0.9 and chlorine's value is 3.0. So we're going to do the bigger one minus the smaller one because electronegativity can never be less than 0, can never be negative. So we're going to do the 3.0 minus the 0.9. It gives us 2.1. So since 2.1 is greater than 1.7, that means that we are dealing with an ionic bond and there will be a transfer of electrons. And so we will get our cation and our anion, and they'll be attracted to each other. So how do we draw these Lewis dot structures to represent ionic compounds forming? There's 4 main steps. The first thing you want to do is you want to make sure you calculate the electronegativity difference to confirm you have an ionic bond. Then what you want to do is you want to draw the structures for the neutral atoms side by side. And what you want to do is also show the electron transfer. So you'll circle electrons going from the metal to the non-metal. And at the very end, you'll draw the ions side by side, attracted to each other. So we have various examples here. The answer key for each is an extra video that you can watch for each of these over here as well. But I'll walk you through how to do Lewis dot structure for the various ionic compounds that we have here. So first we'll do the example with calcium chloride. I'm going to calculate the electronegativity difference just to confirm that it's ionic. So we know chlorine is 3, and that's going to be more electronegative because it's our non-metal. But let's go take a look at what calcium is. Calcium is 1.0. So we do 3.0 minus 1.0 is equal to 2.0. Therefore, ionic, because I should have put this first. 2.0 is greater than 1.7. So it's ionic. So what we're going to do is we're going to draw the Lewis dot structures of our neutral elements. So calcium is in group 2, so there's 2 dots. Chlorine is in group 7, so there's 17, so there's 7 dots there. And it says there's 2 chlorines, so I'm going to make sure I draw those 2 chlorines there. And my calcium is my metal, so it's going to transfer its electrons to the chlorines. The chlorines only need one each, so one electron will go to calcium, or to the top chlorine, and one electron from calcium will go to the bottom chlorine. And so the end result that we have is, what we did is, this was step one, the transfer, or the electronegativity difference. Step two is drawing the neutral elements, and then step three is showing the electron transfer. So this is steps 2 and 3. So really now step 4 is drawing the ions side by side. So I usually put the metal on the left. I put Ca2+, and there's two chlorines, so I put 2, and then I open the brackets, put my Cl there like that, close the brackets, and -1. So there's 2 of those chlorides, and that's it. And so here we've drawn the Lewis dot structure, we've shown the formation, and the final Lewis dot structure for calcium chloride. We can do the same thing for the next example. So you can pause the video and try it yourself, and then check your work to make sure you're on the right track. So the electronegativity difference between Na and O. I know O should be larger because it's the non-metal in terms of electronegativity, so it's 3.5 minus 0.9. So we have 3.5 minus 0.9, and we're going to get 2.6. So since 2.6 is larger than 1.7, this means we have an ionic bond forming. So we have Na and O. We don't know how many to draw, but I'll show you how to figure that out. So this is our first step, doing our electronegativity difference. We're going to draw the neutral atom and do the transfer. So we're going to have Na, and over here we have O is in group 16. So 1, 2, 3, 4, 5, and 6. O needs one valence electron to 2 valence electrons to fill its valence shell, and sodium only has 1. So that won't be enough. We need to make sure we have enough metals to donate electrons to complete the valence shells of all the nonmetals present. So oxygen needs 2. That just means I need 1 more sodium. You can't have any leftover electrons. Essentially, all the metals have to have given up all their electrons, and all the nonmetals have to have their valence shells full. So no leftovers. That's a rule as well. So this one will donate 1 of its electrons to oxygen, and so will this one. I usually put them with the unpaired electrons. And so our final step is drawing the ions. We have 2 sodium ions, and we have 1 oxide ion. And there's our final Lewis dot structure. So let's do the same thing for magnesium and fluorine. So again, pause the video, try it yourself. My first step is going to be to do the electronegativity difference to make sure it is ionic. So fluorine has the highest electronegativity value of 4.0, and magnesium is 1.2. So we have 4.0 minus 1.2, and that gives us 2.8. 2.8 is greater than 1.7, therefore that is ionic. Let's do steps 2 and 3, where we draw the neutral and show the transfers. So we have magnesium, that's in group 2, so 2 valence electrons. Fluorine is in group 17, so 7 valence electrons. Fluorine needs 1, so magnesium will transfer 1 over here, but magnesium still has 1 more to give. So it can still make another element happy, and we're going to just add another fluorine to make sure that magnesium can give all of its electrons up. And so this other electron will go to that fluorine. And so the end result is we get 1 magnesium ion and 2 fluoride ions, charge of -1 each. And so that is how you draw a Lewis dot diagram for ionic compounds. Remember, they form by electron transfer. And if you follow those steps and look at the electronegativity values in your periodic table, it should be pretty straightforward to draw these out. So do practice these ones again. If you want to see them done in a slightly different way, but still the same process, you can watch the videos at the following keys. There are links in the presentation that is found um, over here.